Thank you for having me. My name is Svenja Knappe, and I'm the CTO and one of the founders of FieldLine Medical, and also a research professor in the mechanical engineering department at the University of Colorado in Boulder. And I've spent the last 25 years of my career taking vapor cell-based quantum sensors and trying to engineer them so we can take them out of the lab and into application. And specifically, or one of the big applications I've been interested in was biomagnetic imaging, specifically brain or heart imaging. And we founded FieldLine Medical in 2017, really out of a market pull, which isn't always the case for quantum systems. And so the problem we're faced with when we think about brain disorders is that is a huge prevalence. 1 in 5 people has a diagnosable brain disorder, and that's scary. That's big. It's a big challenge for our society. The global market is about $1 trillion US dollars. $1 trillion in the US, about 16 trillion globally. And if you look at and it's kind of hard to describe brain disorders in terms of economics, but if you look at these disorders, a lot of them are long-term disorders we have no treatment for and we don't understand really well. And so there's a very big need for better tools, specifically non-invasive tools to image for diagnostics, treatment monitoring, to aid therapies. So if we look at brain imaging modalities, here I put spatial resolution onto the vertical axis, temporal resolution on the horizontal. The workhorse we all know is MRI, magnetic resonance imaging, and it images water distribution. So it's not functional, but it tells us where is what. If we're interested in function, and if you looked at these disorders, a lot of functional disorders, we need to look at functional methods. So there's functional MRI, which images oxygen distribution in the brain. Not quite the same resolution as MRI, but here we go. Then we have the radiotracer methods, such as positron emission tomography, where you inject a radiotracer into the body and you can image glucose or some of the proteins. If you're interested in direct electrophysiology, you have electroencephalography, where you glue electrodes to somebody's head. Very high temporal resolution, but very poor spatial resolution. You get a better spatial resolution with a magnetic counterpart, where you measure the magnetic fields coming out of the head. But if you want really, really good spatial and temporal resolution right now, the only option is invasive. You drill holes into the skull and you inject electrodes on the inside. And so one of the hopes we have for some of these quantum imaging we're building is to move this non-invasive magnetoencephalography into that range with very high spatial and temporal resolution to start challenging these resolutions we currently only give with invasive methods. So if we look at how a current magnetoencephalography system, MEG system, looks like, it's here on the left. The top left, you see it's a gigantic helium door, and on the bottom, liquid helium door. At the bottom are superconducting magnetometers embedded in this thing. You stick your head in there. You can see on the top left the photo of somebody's head in there, and you can measure the magnetic field that is naturally coming out of the heads when neurons fire on the inside, because the neural currents create a magnetic field, and your head is transparent to those fields and gets picked up by this array of sensors. If we can build quantum sensors that don't need that cooling, we can move these sensors directly to the skull and create movable systems, but we also get very much closer to the source of those signals, and we get much higher signal amplitudes. And on the bottom, you see, for example, a brain response that we measured on the left with one of those squid-based systems, on the right with one of the quantum sensor-based systems, and they're on the same scale. So you can see much higher signal amplitudes, and it also results in higher SNR, even though our noise floors are still higher. And so the technology we have built is an OPM magnetometer, optically pumped magnetometer, based on laser spectroscopy in vapor cells. And we worked very much on translatable technologies? How can we make these technologies on wafer scale? How can we use these lasers that are telecom lasers for these? And so merging this MEMS technology with atomic spectroscopy is how we created these sensors. And on the right, you see the size. Each sensor is about the size of a AAA battery. The technology timeline has been very long. We made our first small sensors in 2004. And then we really spent 15 years. So the first brain signals we measured in 2009, 2010, and it took a very long time to convince a medical group to adopt a new type of technology. And so this is one of the challenges we face with these new technologies we develop. How do we convince the field of medical doctors that is just doesn't know anything about technology to adopt something they don't know? And so this has been a long path. We first developed this at NIST, then I switched to the University of Colorado, and then in 2017 we founded FieldLine. We're by now on the third commercial device that we sell. We sold our first device in 2019, and we're currently going through FDA approval with this device. And so we had to learn how to scale, how to make a lot of these sensors, and actually how to deal with the user groups. Whoops, this doesn't look so good. This slide does not come out very well. I don't know where pictures went, but contact me if you have questions. Come join our team. We're hiring. We have about 40 installations of these brain systems around the world now. We have about 30 customers all over the world. And yeah, we make thousands of sensors in a year, and it's exciting technology. So I have